okay, it says the equilibrium constant, so you know it's a weak acid. That's what that means. It's a weak acid. Okay, so I can write the general form of the equation. HA is in equilibrium with hydrogen ion plus anion. All right, and the KSP, or the Ka, is going to equal hydrogen times anion over HA. The fact that it's monoprotic means the coefficients are all going to be 1. Okay, so what do we have? Let's build our ice table. Okay, we're starting with 0.075. And at the beginning, hydrogen ion is 0 and anion is 0. If you have questions at any point, please tell me. You're going to make X, subtract X. So the equilibrium concentrations okay. And except it's not going to be, we know something else. We know the pH. If the pH is 3.56, pH is 3.56, that means the hydrogen ion concentration is 10 to the minus 3.56, which is the same thing as 2.75 times 10 to the minus 4. So we can go back and change a couple things. We now know what the X is, right? So this is going to be 2.75 times 10 to the minus 4, 2.75 times 10 to the minus 4. As is this last one. But this one is going to have a negative sign. So that means we can change this. When I subtract out, and it's questionable which way. Wait a minute, this is 0.575. When I make mistakes, you got to tell me, okay? Copying down is one of the hardest things. That's close enough. I decided because it's in this digits here, that I'm going to actually subtract it. And so this number came out to 0.572. So it's not a big change, but a little change. Now I have all my equilibrium concentrations. So now I can do the Ka. That's just going to be the H times the A, so it's going to be 2.75 times 10 to the minus 4 squared like that. And then when I work it out, now a couple things to be careful of on your calculators. Use parentheses generously. When you go to square this number, it needs to be in parentheses, or have it as the answer from the previous problem. The reason is if you just square the end, it'll just square the -4. It won't square everything. And this came out 1.32 times 10 to the -6th. Any question on that? Oh, thank you. I see somebody did, Jasmine, you saw the number was 0.075 was wrong. Thank you.
Yeah.
Yeah, don't hesitate to jump in and call me or speak out. I don't get mad at that. I appreciate that. I'm glad you caught that. Okay, is everybody pretty comfortable with that problem? Do you see how I got the numbers? Now that I have the right numbers. Okay, good. Let's go. I have to change to mouse. Come on. There we go. Now I should be able to move up. Should be and are able are two different things. Okay. And I have to clear this. Okay. Now we're going to do a base. The base is similar. You want the equilibrium constant. Actually, maybe that's the way to do it. Okay, and you have a concentration of the base, and you have a pH. And the fact that it's base, it means the pH should be above 7. Okay, so a general equation for the base is going to be like this. Sorry, I have to move some things. Okay, is going to equal M plus OH minus. Okay, let's do our ice table. Now, the pH is 11.57. That means POH equals 14 minus 11.57, which is going to equal 2.43. Now, why am I changing to POH?
Because we need the concentration of the hydroxide to solve for the equilibrium constant.
Good. Because you're working with the base, you have to work with the hydroxide. So then I want to calculate OH concentration. It's going to be 10 to the minus 2.43, which is equal to 3.72 times 10 to the minus 3 molar, of course. All right. And now just one of the things I learned was to keep looking at my exponents to see if they're reasonable. Especially with calculators, it's easy to make a mistake. The minus 2.43 POH tells me the first digit, the 2, tells me the approximate exponent. So it's going to be around a -2. The 0.43 gives me this number, but when I say this should be -2, it could be plus or -1 on either side. So the -3 is a reasonable value. So that tells me I have this number, the OH concentration, right? And I do expect you to be able to write equations like I've done on these two with the basic chemical equation. And we know this number. These begin with 0. So to get here, I've added this much hydroxyl ion. It's 1 to 1, so I've added this much cation in this case. And I got to subtract. Okay. So this is good. When I subtract these two, 0.379. Now, this time, because I'm working with OH, I'm going to have a KB. The KB equals the cation times the hydroxide ion divided by the concentration of the metal hydroxide. So that's going to be 3.72 times 10 to the -3 squared divided by 0.379. And then this is going to equal 3.65 times 10 to the -5. Any questions? So to do this, you have to always remember that if you have pH, you have POH. If you have pH, you can find hydrogen ion concentration. You can find POH. You can find hydroxide ion concentration. And actually, if you know any one of these, you can find all the others. Okay, ready to go on? Is this too easy for you? I just thought it's better to go over things once more fully with problems. Okay. This is finding those 4 values for each of these solutions. Okay, the first thing I like to do, I have nitric acid. Is it strong or is it weak? Is nitric acid a strong acid or a weak acid? Why don't you answer in chat? Boop, boop, boop. Good. If you know the strongs, then you know the weaks. So this is going to totally dissociate. And if it's strong, what that means is that the hydrogen ion concentration equals the nitric acid concentration because everything dissociates. So if HNO3 is 0.359 molar, that means the hydrogen ion concentration equals 3.59 molar. Then I can find pH. Okay, so pH is going to equal 10 to the minus 0.359, which equals 4.49. Now, technically, I should have 3 significant figures to the right of the decimal point. The reason is 0.359 has 3 significant figures. In the rules of log, because the number to the left of the decimal point refers only to the exponent, this is where you put your significant figures, to the right of the decimal point. Okay, now, saying that, I would probably give credit if you rounded it up, but technically you shouldn't. Okay, POH is going to equal 14.000. Any number of decimal places is fine there because it's an exact number. And that's going to equal 13.555 if I've got my numbers right. And then the hydroxide ion concentration is going to equal 10 to the minus 13.555, which equals 2.786 times 10 to the minus 14 molar.
Wouldn't the POH be 9.551?
14, yeah, I guess it would be. Thank you. I made a mistake on my calculation. Okay, what was that again?
It's 9.551.
9.551. Yeah, when I look at 14 minus 4, it should be around 10, right? Good thinking. Thank you.
But to find the pH, don't you take the negative log rather than raising 10?
Yes, thank you. It's harder when I'm doing this in front of people. Yes, it is the log of 0.359, which is 4.449. Thank you. Okay, so this is, we'll have to, do you have the noises you hear are my dog. She thinks I should be giving her attention. -9. And does anybody have what that concentration equals?
What are you asking for?
What 10 to the minus 9.551 is?
It would be 2.812 times 10 to the negative 10th power.
Okay, good. Thank you.
You're welcome.
Okay. So now that I've confused everybody, do you see what to do there? Any questions? Okay.
I think the pH would technically be different if you take the negative log as opposed to raising 10. So I think it's like
Oh.
0.44 rather than
Boy,
4.44.
0.3, let's see, I want the log of 0.359. I don't know why I did that. Yes, it'd be 0.44. Same number, but. And so then you would make this 5. So this is going to be changed, isn't it? See how easy it is to make mistakes? Okay, so if we subtract we've got 13.55, right? 1. So the hydroxyl is 10 to the minus 13.551. So that's going to equal 10. $2.812 times 10 to the minus 14. And we want 3 significant figures there. Does that look better?
Yes, thank you.
No, thank you. I'm glad you caught that. It's so easy to make mistakes on this stuff, and that's why you need to go back and check. Is everybody okay with that and understand? Okay, then let's look at the base. Lithium hydroxide, strong or weak? Okay, let's hear from some of the rest of you. Yes. Okay, so we know it's strong. So we know that means that this goes to lithium ions plus hydroxide ions. Everything's 1 to 1. And so it means that the lithium hydroxide concentration equals the hydroxide ion concentration. So the POH is going to be the log minus the log of that, which I think I got right this time. Zero 0.253. Okay. Then I can find pH is 14.00.
How did you get POH?
POH, I took the log of 0.559. Do you see that?
Yeah, thank you.
Okay. 0.253. So the pH is 13.00. 14.747. And that makes sense because this is a strong base and it's fairly concentrated. So the hydroxide ion should be fair, or the hydrogen ion should be uh, a small concentration, but a large pH. And now I can find the hydrogen ion. And that's going to be 2.786 times 10 to the minus 14. And it should be really 3 significant figures. And that's molar. Anytime you have concentration, you should put the capital M for molar. Everyone with me?
Did you get 2.79 or 1.79?
Well, let me see. Let's see, I've got pH, so it's 10 raised to the minus 13.747. I've got 1.79 now. Okay.
Thank you. I just wanted to make sure my calculator was working properly.
No, I'm glad you point that out. It just, once again, it shows how easy to write a number wrong. Okay? So on your quiz and your test, what it says is you got to go back and check numbers carefully. And if I had a mistake like that on a quiz or test, it would be a small mistake. If I see the work, see that you understood what you were doing and were doing it mostly right, you don't lose much on that. Okay? Everybody fine with that? Okay, let's go to the next problem. HF, strong or weak? Strong or weak? Okay, good, weak. So that means it's equilibrium. So HF is going to be an equilibrium with hydrogen ion plus fluoride ion. Now, this is where you're going to have something else. You don't have quite enough to solve this problem, do you? It's not given there, and that's deliberate. If it's a weak acid, it means I need an ice table and I need a Ka. Where do I get my Ka? Anybody know where to get the Ka if it's not given?
Look it up.
Yeah, look it up. There's one in the back of your textbook. Okay, so you can look there. Sapling has them in their resources. And there's usually that's called acid dissociation constant. You can get it off the net, but that may actually be a harder place to find it. You want a table value because temperature is also critical in this. So I'm going to look that up, and I'm also going to just write down Ka is going to equal hydrogen ion concentration times fluoride ion concentration over HF. And it's going to equal 3.5 times 10 to the minus 4. Okay. One thing too, the minus 4 tells you it's also weak in that something that the stronger the acid, the higher the value of the exponent. It's going to be -1, -2, or much stronger than -4. Okay, so we have to build the ice table. And I didn't plan my space right, so I'll have to write it out again. Okay, so what do we know? Initial concentration is 1.5 molar. Initial concentration of the ions is 0. We're going to form X. The stoichiometry tells me that it's 1 to 1 to 1. So I get my change. Then my equilibrium constants will be, or concentrations will be those values. So then I can say 3.5 times 10 to the minus 4 equals x squared over 1.5. And I'm going to make this say here, I'm going to assume something. And if you make this assumption, you have to write it down. In other words, if you don't write that down, you'll lose points. I'm going to assume that x is going to be much smaller than 1.5. And so my denominator is just going to be the 1.5. So then 3.5 times 10 to the minus 4 times 1.5 is going to equal x squared. And I got to check my numbers, 4.25 times 10 to the minus 4 equals x squared. And the square root 0.0229 molar is x squared, which also equals H plus, which also equals F minus. Is that what you got?
Yep.
Okay, then you take, oh wait, we're not to the, it does not equal this yet, does it? Because what do I have to do? This is x squared, so I have to find x. I take the square root of this number, which, wait a minute, this is x squared, sorry.
Yeah, you already square rooted it.
So I was right. So x, yeah. So that's my hydrogen ion concentration. Okay, so pH will then equal 1.64. pOH equals 14 minus 1.64, which is 12.36. Is that right? Yeah. Okay. And the hydroxyl ion concentration equals 10 to the minus 12.36, which equals, let me make more room for myself. 4.37 times 10 to the, wait a minute, did I get that right? No, I'm looking in the wrong place. Which problem am I at? Yeah, 4.37 times 10 to the minus 13 molar. Does everybody see that okay? Any questions? Now, it is, while mathematically 10 to the minus 12.36 is okay to write, that's how we're going to get it. When you get to writing the number, you should write it out because this is more useful for people. So everybody's with me? You ready for the next problem? Is this helping you to get more confident in what we're doing?
Yeah.
Yes, thank you.
A lot of this is learning to read the problems. And what I've found is if you get weak acid pretty well, weak acid base calculation, the rest of the calculations in the next chapter are much easier because you're starting to see how you read things. Okay, the next problem, I've got 0.2 molar ammonia. Strong or weak? Okay. This is another, it's a weak base because it's not on the list of strong bases. And so it's in equilibrium with NH4 plus OH minus. And I should have stuck a water in here, right? Okay, so that means I have a KB that's equal to NH4 plus times hydroxide ion divided by ammonia concentration. Now, what other piece of information do you need? If you're going to find hydrogen ion concentration, hydroxide ion concentration, what's the variable that's in this equation that you don't have yet?
KB.
KB. So you have to look that up, and KB is going to equal 1.8 times 10 to the minus 5. The danger, if you just Google it and you get say somebody's problem, if they've made a mistake on their KB or it's done at a different temperature and you don't see that, then your answer is going to be wrong. So I really suggest going to a table. One place that you can get good information, but your book is really the easiest place to get KBs. But another site that helps sometimes is Wolfram Alpha. Actually, there's no, if you're familiar with Mathematica, if you used that in your class, it's the same group that made Mathematica. They have a database search engine, and all it does is look at databases. So you could probably put KB in of ammonia, and I'd write NH3, capital N, capital H3, Ka, and usually it'll come up with what you want. So if you're someplace where you don't have the book, the nice thing with our textbook, you can keep it on your phone. Okay, so weak base, we need to go to an ice table. At least I'm going to the ice table. You don't have to. There are other ways to solve these problems. It's just bookkeeping. So 0.02 molar, and I don't need to write the M in there. Starts off at 0, plus X, plus X, plus X, X, minus X. 0.02 minus X. Now, I'm going to make an assumption that X is much less than 0.02. Okay? It's close with this being minus 5, but that really puts the decimal place out of ways. If I don't make that assumption, what kind of problem do I end up with mathematically?
Quadratic equation.
Quadratic, and you have to use your quadratic formula, which I mean, that happens and you have to work through the math. But the math, if you can make that assumption, the math is much easier. Okay. So 1.8 times 10 to the minus 5 equals x squared over 0.02. Isn't that a lot nicer than the quadratic? So 1.8 times 10 to the minus 5 times 0.02 equals x squared. 6.0 times 10 to the minus 4 equals x squared. Or wait, I'm skipping. That makes more sense, times 10 to the minus 7 equals the square. And then 6.0 times 10 to the minus 4 equals molar equals X. And that X is going to be hydroxide ion concentration. So the POH is equal to, I want to check this. Whoops. Come on, find me. Is going to equal okay. Log. Okay, what did you get for the POH?
I got 3.2.
3.2, okay? That's looks about right. 3.20. So pH will equal 14 minus 3.20. Which is going to be 10.8. And then your hydrogen ion concentration is going to be 10 to the minus 10.8. Which is about 1.58 times 10 to the minus 11. And we only really have one significant figure. Or 2 times 10 to the minus 11 would be acceptable. I would accept any of those. Okay. Now, can you do the acid-base questions now? Do you think? Okay, now remember, there is another way to change between these, and that's using KW. Remember, KW equals hydrogen ion times hydroxyl ion. And you can solve using that. So 10 to the minus 14 the reason I usually use POH is the calculation is simpler. It just is a little easier to subtract whole numbers than working with 10 to the minus 14. But either way is legitimate. If I wasn't changing to pH or POH, then I would just use this part. But since I'm changing, I like to make life easy for myself. Okay. Now, shifting gears a little bit. This is what we talked about the other day too. Okay, in the following substances. They're dissolved in water. Predict whether the pH will be acidic, basic, or neutral. And if it's basic or acidic, you need to write the equation. So what we have to do is break this into anion and cation. So I'm going to draw a line down here just for my purposes. Sodium, is that part of a strong base or a weak base? If you had sodium hydroxide, would it be strong or would it be weak? Okay, good, strong. Anywhere the metal cation is in the first group, it's going to be strong, and 3 of the second group are strong. Anything else is weak. So this is strong. Now the bicarbonate, HCO3, is that strong or weak? Okay, weak. So that means there will be hydrolysis with the bicarbonate. So HCO3 is the part that's weak. It can react with water, and I'm going to draw water this way because it helps me to see what's happening. This can form H2CO3, carbonic acid, which is a weak acid. When this picks up the hydrogen, the thing that's left over is hydroxide ion. Do you see that? So is that solution going to be as acid or base? Acidic or basic? Thank you for showing a response. Is it going to be? Yeah, that's right. It'll be basic because the hydroxide ion is left over. Okay. Ammonium chloride. Let's separate the ion from the cation. Now, ammonium ion, is that part of a strong base or a weak base? Okay, it's a weak base. How about chloride ion? Strong or weak? Okay, how do you know whether it's strong or weak? What do we use? You use the list that I gave you of strong acids and bases and weak acids and bases. Or actually, sorry, if you know the strong acids, you know the strong base. If it's not on that list, you can assume it's weak. So let's take the ammonium ion plus water, and it's in equilibrium because it's weak. It's going to form NH4OH, and it will leave off hydrogen ion. So if I have hydrogen ion left, is it going to be acidic or basic? Right, this is acidic. Now I want you to think through the next one, lithium chloride. And I want you to put in the chat, is it going to be acidic, basic, or neutral? Good. So you see that lithium is the cation for a strong base. Chloride ion is the anion for a strong acid. So there's no reaction, and I can put NR to indicate that, and it's neutral. Okay, what about potassium acetate? See if you can figure out if there's a hydrolysis. Write the equation and tell me if it's basic or acidic. You only have to tell me on the thing if it's basic or acidic or neutral. Okay. The acetate is going to be the part hydrolyzed, right? And it will react with water to form acetic acid or acetic acid plus OH minus, so it is basic. So are you beginning to get the idea of how to sort through those? Okay. Now, you feel fairly comfortable with this chapter, I hope. I am not going to cover titrations. I didn't put a buffer problem on, but it's basically the weak acid problem. So you only have to worry about identifying buffers and finding the pH of a buffer or whichever part's missing from the Henderson-Hasselbalch equation. But I will not do the titration portion. Okay, so I'd like to just start the solubility equilibrium. Okay, what happens when we say something is insoluble? That means that in practical aspects, it's not soluble. We can't see much difference. But the reality is that some ions will dissolve, although it's going to be very small. So a strong electrolyte dissociates completely. A weak electrolyte has minimal dissociation, but we can still write an equilibrium for it. And we can calculate the equilibrium constant. Now, the equilibrium constant, when we deal with solubility, it's just a special version of it, and it's called the solubility product constant. And we use the term KSP to say solubility product. Now, if I have an ionic compound, and this is just a general form, that can be the way I show solubility is it starts off as a solid, and then it can dissociate to some extent into the ions. I didn't write that very well. And we're just going to say we don't know the charge because it is a general form at this point, plus M anion. So the ions are aqueous, the solid has the S. Now the KSP, and I'm going to write that over here so there's more room. The KSP is just going to have the aqueous parts, not the solid. So it's the metal ion raised to its power times the anion raised to its power. Why don't I have a denominator?
Because the reactant is a solid.
That's right, because it's solid, so we don't include that. Okay, so I want you to try writing the reaction for barium sulfate. Okay, so I'm going to get barium ion plus sulfate ion. Everything's 1-to-1 there, right? So what's the KSP going to equal?
Ba2 plus SO4.
Now, it's not plus, is it? It's times. Okay, thank you for answering. And I'm saying that because I want to make sure you get that idea. I've had students sometimes put plus. Everything in equilibria is times. So in some ways, this is a little easier than weak acid, isn't it? Because you don't have the denominator to worry about. Okay, try the next one, the barium phosphate. Write the reaction. And then the formula for the KSP. So everybody see how to do that? Anyone having trouble? Now remember, KSP is not the same thing as solubility. The term solubility refers to the amount of a substance that dissolves to form a saturated solution. Usually the units are grams per liter or moles per liter. So the KSP is not the word solubility. It's the solubility product. But we can use it to find molar solubility. So let's try a problem. What is the KSP for calcium fluoride, the KSP for calcium fluoride is 3.9 times 10 to the minus 11 at 25 degrees C. What is the molar solubility? That means I want the concentration of this. That's my unknown. So I start, the first thing you have to do is write the equation. So my KSP is going to equal that. Okay, let's do an ice table. Now, because the calcium fluoride is solid at the start, we don't have any part of that enter into the calculation. But this starts off at 0. Fluoride is going to make plus 2x, right? Calcium plus x. Is there anyone who does not see where the 2x comes from? Okay. So now I substitute these values into my KSP equation. So we've got 3.9 times 10 to the minus 11 equals X for calcium, 2X for fluoride. If you don't get this coefficient inside the parentheses, you make a common mistake. So this part is going to equal X times 4X squared. So that's going to be 4X cubed. So I'm going to divide both sides by 4. Now, when you take a cube root, depending on your calculator, you can do it one of two ways. One is sometimes they have a function for taking roots higher than square root. If they don't, the other way you can do it, which works on any calculator that has exponents, take 10 to the minus 12 and put that in parentheses and then raise that to the 1/3 power and put, You may or may not have to put parentheses. I like to put the parentheses because I'm sure then that it looks at it as 1/3. The 1/3 power is the same thing as the cube root. And I've actually found on most calculators now, I like this method better just because I don't have to worry about the order I put stuff in as much. So this comes out to 2.1 times 10 to the -4 molar, and that's going to equal the calcium concentration. And if we look at our equation, there's 1 mole of calcium fluoride and 1 mole of calcium ion. So the solubility is based on the stoichiometry for the calcium fluoride. So that's going to equal the calcium ion. And if I wanted the fluoride concentration, it's just going to be 2 times that. Any questions about that kind of problem?
What would the units be for the molar solubility?
Molarity. We're going to do molar solubility is moles per liter. And I'm going to stick to molar solubility. To get the grams, you would multiply by formula weight. But I think if you get molar solubility, you're doing just fine. This to me is a little easier than the acid base calculations. I don't know, you may not find it that way, but to me it seems more straightforward for right now. Okay? With that, and any questions? All right. The other thing I want to talk about today is the relationship to the common ion effect. What happens if in this calcium fluoride that we just did, I had a common ion? We find that if you have a common ion, and in this case, they added some sodium fluoride to it, the x-axis is sodium fluoride, the y is the calcium fluoride. So they're looking at how the solubility changes as you add some common ion. And what you find is it changes really rapidly and it decreases the solubility. So if you add either calcium ion or fluoride, calcium fluoride becomes less soluble. So what does that mean in terms of the calculation? Well, first thing, we got calcium fluoride in a 1/100th molar solution. Okay. So the basic equation is the one that's insoluble. Okay, calcium nitrate, all nitrates are soluble. So that does not have an equilibrium, but calcium fluoride does. So we're going to start with the equation for the one that stays insoluble. There's what we consider to be insoluble. Or the weak acid, it's the same kind of idea. 2 fluoride ions. That's aqueous, aqueous. Okay? That looks exactly the same, right? And my KSP is going to still be calcium ion times fluoride ion. Now, make my ice table. This part we don't do because it's all insoluble. Now at the beginning, there's no extra fluoride ion, but there is some calcium ion at the beginning. There's 0.010 molar. So we're going to have plus X plus 2X. Okay. So now the KSP is going to equal X by 0.0, wait a minute. I got too fast there. 0.01 plus X. Now, this time we're going to make an assumption that X is much, much less than 0.01. Do you see why we do that? It makes our calculation easier. And we know that this is the same value as before. 3.9 times 10 to the minus 11. That, come on. This number is much larger than 10 to the minus 11. Okay, come on. There we go. So the KSP is going to equal this time 0.010 times 2x squared okay? So that's 0.040 x squared is going to equal 3.9 times 10 to the minus 11. X squared is going to be 3.9 times 10 to the minus 11 divided by 4. Okay. That's going to be 9.75 times 10 to the minus 12. So X will equal 3.12 times 10 to the minus 6th molar, and that's your calcium ion. Did I get the numbers right? Okay, good. Thank you. Okay, so how did that compare with the previous problem? In the previous one, calcium had 2.1 times 10 to the minus 4 molar, right? And now you've got 3.1 times 2 times 10 to the minus 6. Minus 6 is a lot smaller than minus 4. That adding that initial calcium changed the concentration fair amount. So that was significant. Any questions? You see why you have to have algebra for this class? No questions? Did this help you today, do you think?
Yes.
You like this method? Okay, next time on Wednesday, we will do the Lewis acids and finish up the solubility chapter. There's Lewis acids and complex ion formation, so that you know where I'm going. And then on Thursday, I'll send you I'll do a quiz in Canvas. And I think they changed Canvas so that I can have you, for each question, submit a file. And so I think I'll have you put the picture in the file, and it's a little more picture taking for you folks, but it will be a lot easier for me. You saw the test grades were up, I assume. I hope you could see them.
We can't see the answers though. Is there a way that we can get feedback?
Oh, because I wrote a lot of feedback. Okay, I'll try to do something to give you feedback. You can't see the things I wrote about at each question?
No, it says all the answers are hidden, so I don't think that you can see it, but I may have missed something, but it looks like it's all hidden.
Okay, go in. I'll try to see what I can do to make that visible. And if not, I'll try to send you it may take, if I have to write it out separately, it may take me a couple days to do that, but I will do that to make sure you get the comments.
Thank you.
Okay, I'm glad you told me. All right. If you have no questions, I guess that's it for today then. Have a good day, and I'll see you on Wednesday again, unless you have questions.
You too. Thank you.
You're
you.
welcome. Have a good day.
You
After
too.
how
Thank
long?
you.
And if it's more than an hour, then I'll just pick